Section: Introduction. In this section, we introduce multi-layer perceptrons, MLP, which are also referred to as fully connected feed-forward neural networks. These networks serve as essential components in contemporary deep learning models. MLPs are structured with several layers of nodes, where each node, or neuron, applies a specific activation function to a weighted sum of its inputs. This design enables MLPs to approximate a broad spectrum of nonlinear functions, a capability supported by the universal approximation theorem. Consequently, MLPs are widely utilized in various deep learning applications, such as classification, regression, and feature extraction. However, despite their versatility and common use, MLPs have some drawbacks, including challenges in interpreting the learned representations and limitations in scaling the network. Kolmogorov-Arnold networks, KANs, offer an innovative alternative to traditional MLPs by utilizing the Kolmogorov-Arnold representation theorem. Unlike MLPs, which use fixed activation functions at the nodes, KANs incorporate learnable activation functions on the edges, substituting linear weight parameters with univariate functions that are defined as splines. This approach leads us to explore KANs as promising alternatives to MLPs. We recognize that current comparison experiments between KANs and MLPs are not conducted fairly, as they often involve different parameters or floating point operations, flops. To investigate the potential of KANs, we believe it is crucial to compare KANs and MLPs under equitable conditions. Therefore, we control the parameters or flops of both KANs and MLPs, and then we train and evaluate them across various tasks, including symbolic formula representation, machine learning, computer vision, natural language processing, NLP, and audio processing. Through these fair comparisons, we find that KANs outperform MLPs only in tasks related to symbolic formula representation, while MLPs generally perform better in other areas. We also discover that KAN's success in symbolic formula representation is due to its use of the B-spline activation function. Initially, MLPs lag behind KANs in overall performance, but when we replace the activation function in MLPs with B-spline, their performance matches or even exceeds that of KANs. However, we note that B-spline does not enhance MLP performance in other tasks, such as computer vision. Additionally, we observe that KANs do not necessarily outperform MLPs in continual learning tasks. The original KAN paper compared KAN and MLP performance in continual learning using a series of one-dimensional functions, where each function was a translation of the previous one along the number line. We, however, assess their performance in a more standard class incremental continual learning setting. With fixed training iterations, we find that KANs experience more significant forgetting issues compared to MLPs. We hope that our findings will provide valuable insights for future research on KANs and other alternatives to MLPs. Next, we outline the formulation of KANs and MLPs. KANs consist of two branches, the B-spline branch and the shortcut branch, which combines a nonlinear activation with a linear transformation. In the official implementation, the shortcut branch uses a CELU function followed by a linear transformation. Let's denote the feature vector for one sample as x. The forward equation for the spline branch of KAN can be expressed as a matrix operation involving the spline function applied to the input. This spline function operates element-wise, meaning each element in the input matrix undergoes a different nonlinear transformation, although they all follow the same template with varying parameters. In the original KAN architecture, the spline function is specifically chosen to be the B-spline function, and its parameters are learned alongside the other network parameters. In contrast, the forward equation for a one-layer MLP with a nonlinear operation can be similarly expressed, differing only in the type of nonlinear function used. Thus, aside from the interpretation provided in the original KAN paper, we can also view KAN as a type of fully connected layer that applies an element-wise nonlinear function followed by a linear transformation. The differences between KANs and typical MLPs can be summarized in two main aspects. 1. the nature of the activation functions, where MLPs typically use fixed activation functions without learnable parameters, while KANs utilize spline functions with learnable parameters that vary for each input element. And 2. The sequence of operations, where MLPs generally perform a linear transformation followed by a nonlinear transformation, whereas KANs perform a nonlinear transformation first, followed by a linear transformation. To some extent, we can also describe the fully connected layers in an MLP as first nonlinear, then linear. For instance, in an MLP, we can equivalently describe it as having fully connected layers with a nonlinear operation last and a linear head, or a linear tail with fully connected layers that apply a nonlinear operation first. Among the differences between KANs and MLPs, we believe that the variation in activation functions is the key factor that distinguishes KANs from MLPs. We hypothesize that this variation makes KANs and MLPs suitable for different tasks, leading to functional differences between the two models. To test this hypothesis, we compare the performance of KANs and MLPs across various tasks and identify the specific tasks each model is best suited for. To ensure a fair comparison, we first derive the formulas for calculating the number of parameters and flops for both KANs and MLPs. In our experiments, we control for either the same number of parameters or flops to accurately compare the performance of KANs and MLPs. Section Summary. In this section, we introduce multi-layer perceptrons, MLP, as essential components of deep learning, highlighting their ability to approximate nonlinear functions but noting their limitations in interpretability and scalability. We then present Kolmogorov-Arnold networks, KAN, as a promising alternative that utilizes learnable activation functions, and we outline our comparative analysis of KAN and MLP across various tasks, revealing that while KAN excels in symbolic formula representation, MLP generally outperforms KAN in other domains. Section: Number of parameters of KAN and MLP. In this section, we discuss the number of parameters in KAN and MLP. We denote the input and output dimensions of the neural network layer as D-in and D-out. The order of the spline, which we refer to as K, corresponds to the parameter K in the official NN module KAN layer. This order indicates the degree of the polynomial basis in the spline function. We also use G to represent the number of spline intervals, which aligns with the num parameter in the official NN module KAN layer. This number reflects the count of B-spline intervals before padding, which is one less than the number of control points. After padding, we have a total of K plus G functioning control points. The learnable parameters in KAN consist of the B-spline control points, shortcut weights, B-spline weights, and bias. The total number of learnable parameters can be expressed as the product of D-in and D-out multiplied by G plus K plus 3 plus D-out. In comparison, the learnable parameters for a single MLP layer are the product of D-in and D-out plus D-out. Next, we evaluate the flops for KAN and MLP. In our assessment, we consider the flops for arithmetic operations to be 1 and for Boolean operations to be 0. The operations in the de Boer-Cox algorithm at order 0 can be converted into a series of Boolean operations, which do not require floating point operations. Therefore, theoretically, its flops is 0. This differs from the official KAN implementation, which converts Boolean data back to floating point data for operations. We calculate the flops for one sample. The B-spline flops using the de Boer-Cox iterative formulation in the official KAN code, along with the flops from the shortcut path and the merging of the two branches, gives us the total flops for one KAN layer. For one MLP layer, the flops can be expressed as 2 times the product of D-in and D-out, plus the flops from the nonlinear function multiplied by D-out. The difference in flops between a KAN layer and an MLP layer with the same input and output dimensions can be articulated as follows. If the MLP performs the nonlinear operation first, the first term becomes 0. Our objective in the experiments is to compare the performance differences between KAN and MLP while keeping the number of parameters or flops constant. We conduct experiments across various tasks, including machine learning, computer vision, natural language processing, audio processing, and symbolic formula representation. All experiments utilize the Atom optimizer with a batch size of 128 and learning rates of either 0.001 or 0.0001. We perform all experiments on a single RTX 3090 GPU. In the performance comparison for machine learning, we conduct tests on 8 datasets. We use both KAN and MLP with 1 or 2 hidden layers, adjusting the input and output dimensions based on the datasets. The hidden layer widths for MLP are set to 32, 64, 128, 256, 512, or 1024, using JELU or ReLU as activation functions, and normalization layers are included in the MLP. For KAN, the hidden layer widths are 2, 4, 8, or 16, with the number of B-spline grids set to 3, 5, 10, or 20, and the B-spline degrees are 2, 3, or 5. To balance the potential advantages of normalization layers in MLP, we expand the range of KAN spline function beyond the original range of -1 to 1, testing ranges of -2 to 2 and -4 to 4. All experiments are trained for 20 epochs, and we record the best accuracy on the testing set during training. The upper envelope of all recorded points is plotted in the figures for parameters and flops. In our findings, MLP generally maintains an advantage, outperforming KAN in 6 out of 8 datasets. However, we note that on one dataset, MLP and KAN performed nearly equally, while KAN outperformed MLP on another. We plan to conduct an architecture ablation in the next subsection to analyze the reasons behind KAN's advantages in these cases. Overall, MLP shows a general advantage over KAN in machine learning datasets. For computer vision, we conduct experiments on 8 datasets, again using KAN and MLP with 1 or 2 hidden layers. The input and output dimensions are adjusted according to the datasets. The hidden layer widths for MLP remain the same as in the previous experiments, and no normalization layers are used. For KAN, we maintain the same hidden layer widths and B-spline configurations. All experiments are trained for 20 epochs, and we record the best accuracy on the testing set. The upper envelope of all recorded points is plotted in the figures for parameters and flops. In this case, KAN spline functions did not provide an effective advantage, as its performance consistently lagged behind MLP with the same number of parameters or flops. In our audio and natural language experiments, we test on 2 audio classification datasets and 2 text classification datasets. We use KAN and MLP with 1 or 2 hidden layers, adjusting the input and output dimensions accordingly. The hidden layer widths for MLP are the same as before, and normalization layers are included. For KAN, we keep the hidden layer widths and B-spline configurations consistent. All experiments are trained for 20 epochs, except for the Urban Sound 8K dataset, which is trained for 40 epochs. We record the best accuracy on the testing set, and the upper envelope of all recorded points is plotted in the figures for audio and text. In both audio datasets, MLP outperforms KAN. In text classification, MLP maintains an advantage on the AG News dataset, but on the COLA dataset, there is no significant performance difference between MLP and KAN. When controlling for the same number of parameters, KAN seems to have an edge on the COLA dataset. However, due to the high flops required by KAN spline functions, this advantage does not hold when controlling for flops, where MLP appears superior. Thus, we find no consistent answer regarding which model is better on the COLA dataset. Overall, MLP remains the preferred choice for audio and text tasks. Finally, we compare KAN and MLP on 8 symbolic formula representation tasks. The functions to be fitted are sourced from the original KAN paper. We use KAN and MLP with 1 to 4 hidden layers, adjusting the input and output dimensions accordingly. The hidden layer widths for MLP are set to 5, 50, or 100, with JLU or ReLU as activation functions, and no normalization layers are used. For KAN, the hidden layer width is 5, with the number of B-spline grids and degrees varying as before. All experiments are trained for 500 epochs, and we record the best root mean square error, RMSE, on the testing set. The lower envelope of all recorded points is plotted in the figures for parameters and flops. When controlling for the number of parameters, KAN outperforms MLP on 7 out of 8 datasets. However, when controlling for flops, KAN's performance is roughly equivalent to MLP, outperforming it on 2 datasets and underperforming on 1. Overall, for symbolic formula representation tasks, KAN demonstrates better performance than MLP. Section Summary. In this section, we analyze the number of learnable parameters and flops for KAN and MLP architectures, highlighting that KAN generally has more parameters due to its B-spline components, while MLP tends to outperform KAN across various tasks, including machine learning, computer vision, and audio processing, although KAN shows competitive performance in symbolic formula representation tasks when controlling for parameters. Our experiments reveal that while MLP maintains an overall advantage, KAN can excel in specific scenarios, particularly when the number of parameters is considered. Section: Architecture Ablation. In this section, we explore the differences between KAN and MLP based on our experiments. We find that KAN is better suited for representing symbolic formulas, while MLP excels in areas like machine learning, computer vision, natural language processing, and audio processing. To understand the specific components that contribute to these differences, we conduct ablation studies on the architectures of KAN and MLP. We perform these studies using 2 computer vision datasets and 2 machine learning datasets, and we illustrate the architectures involved in our experiments. KAN combines KAN layers with fully connected layers, so our first ablation experiment involves using only KAN layers without any fully connected layers. We note that a KAN layer functions as a fully connected layer with a special B-spline activation applied before the linear transformation. Therefore, we also compare MLP models that use B-spline activation either before or after the linear transformation. Our observations reveal 2 main points. First, in the computer vision datasets, MLP models using spline activation functions show minimal improvement. The higher computational cost of these spline functions makes them less favorable compared to traditional activation functions like ReLU or JLU. Second, in machine learning tasks, substituting the activation functions in MLP with spline functions leads to a significant performance increase. Initially, MLP performed worse than KAN on these datasets, but after using spline functions, MLP's performance became comparable to that of KAN. This suggests that the performance boost for KAN in machine learning tasks largely comes from the use of spline activation functions. We also find that whether the linear transformation occurs before or after the spline function does not greatly impact the final performance, nor does it matter if the spline activation is applied to all input-output pairs or just to inputs or outputs. We further assess MLP's performance with B-spline activation functions in symbolic formula representation tasks. In this experiment, we set the hidden layer width of MLP to either 10 or 20 to balance the additional parameters and computational load introduced by the B-spline function, keeping all other settings consistent with previous experiments. The results indicate that while KAN generally outperformed MLP in earlier symbolic formula representation tasks, MLP with B-spline activation can either match or exceed KAN's performance in all such tasks. This supports our hypothesis that the functional differences between KAN and MLP arise from the distinct activation functions they utilize, making each architecture better suited for different tasks. Next, we examine continual learning. The original KAN paper established that KAN performs better in the continual learning of one-dimensional functions, and we confirm this in the context of computer vision by setting up a standard class incremental scenario. We divide the MNIST dataset into 3 tasks based on digits. The first task involves classifying digits 0, 1, and 2. the second task involves digits 3, 4, and 5, and the third task involves digits 6, 7, 8, and 9. We train both KAN and MLP models on these tasks sequentially, using the same training hyperparameters as in our vision experiments, but limiting the training epoch for each task to just one. The results show that KAN does not have an advantage in continual learning for computer vision tasks. It forgets information faster than MLP, with its accuracy on the first two tasks dropping to 0 after training on all three tasks, while MLP maintains acceptable accuracy on the first two tasks. We calculate average accuracy and backward scores using consistent methods. In the related work section, we note that significant advancements have been made to KAN networks. In KAN, the nonlinear activation originally found in MLP is implemented using B-spline functions. The locality and adjustable grid number in B-splines allow KAN networks to achieve a degree of dynamic architecture and continual learning. Various studies have replaced B-splines with other functions like Chebyshev polynomials, wavelet functions, and orthogonal polynomials, each imparting unique properties to KAN networks. Additionally, there have been efforts to integrate KAN with popular network structures for various applications, such as combining KAN with convolutional networks and vision transformers for improved classification, merging KAN with UNet for medical image tasks, and integrating KAN with GNN for graph-related tasks. However, unlike these works, we do not propose any enhancements to KAN. Instead, we aim to provide a fair and comprehensive comparison between KAN and MLP to offer valuable insights for future research.